Hello everybody, welcome to our talk. In this session I will present a paper named as Stealthy Attack on Algorithmic-Protected DNNs via Smart Bit Flipping. This work has been done in Simon Fraser University at Reconfigurable Research Lab. As you know, recently deep learning have achieved an amazing success in many areas, especially in computer vision and speech recognition. With respect to their great performance and autonomous nature, DNNs have been recently deployed in critical systems such as personal identity recognition, self-driving cars, aircraft control, and medical devices. As a result, it is very important to study the vulnerability and safeguard of such DNN-based systems under various attacks. Recently, DNNs were found vulnerable to adversarial example attacks, which could fool a DNN to misclassify crafted inputs with imperceptible perturbation. For example, in this figure, as you can see, the DNN classifier can work normally for clean inputs, where it cannot predict correctly the input if the adversarial perturbs a little bit of input image. In fact, adversarial examples are inputs to machine learning models that an attacker has intentionally designed to cause the model to make a mistake. It is very important to note that such attacks are stealthy and hard to notice for a user who only has access to original clean inputs. Thus, they are more harmful and have raised serious concern in the research community. In this regard, to improve the robustness of DNN models against adversarial examples, various algorithmic defense mechanisms have been introduced thereafter. The state-of-the-art adversarial defense trained the DNN models using both clean and adversarial examples. As a result, when confronted with adversarial examples, such trained DNN models would behave more robustly and normally. In addition to adversarial example attack, which is a kind of external threat, there is another type of internal threats for DNN models. Especially recently, some researchers demonstrate the vulnerability of DNNs against adversarial parameter perturbation using intentional memory fault injection. As you know, hardware is prone to various faults such as computing logic, error in cache, and there are some new kinds of attack against memory such as row hammer. In fact, the main focus of this type of attack is reducing the overall DNN prediction accuracy classifier to be as low as random guess. In this paper, we'll focus on a main research question. Actually, we answer the question that Are protected deep neural network vulnerable to adversaries exploiting hardware-based faults? In this regard, we formulate a new stealthy attack as a mathematical optimization problem. I mean, we throw a smart bit flipping of the weights. We aim to reduce the DNN robustness under the constraint that its accuracy loss maintain below a perceptible threshold. Actually, the objective of this attack is that to figure out how to flip certain DNN weights bits in a way such that it significantly reduces the robustness of a protected DNN while causing negligible accuracy loss. The assumption of or purpose stealthy attack are as follows. At first, we focus on quantized deep neural network, which are usually deployed in modern deep learning embedded application. Second, we assume that before deploying a DNN model in inference stage, an efficient method is in place to protect it against conventional adversarial example attack. Third, we assume that the attacker has enough information about the DNN architecture and particularly its weights parameter, as well as the hardware structure of the deployed platform. Fourth, we assume that the adversary could potentially attempt to imperceptibly manipulate the input image. In fact, some research work showed that the feasibility of such modification for the state-of-the-art vision classifier and, for example, for face recognition model. At last, similar to traditional bit flip attack, we also assume that the adversary will attempt to precisely inject a small amount of fault into the computing memory system that is deployed for DNN inference. While the number of weight bits in a DNN model ranged from thousands to millions, due to this long execution time, it is impractical to explore the impacts of all bit perturbation on a DNN model. Therefore, to find the most vulnerable bits precisely and effectively, we introduce an iterative method based on a gradient ranking and iterative search. In this proposed method, in each iteration, the algorithm finds the top most vulnerable weights in each layer through gradient ranking. To do so, we compute the gradient of adversarial robustness function with respect to weight bits and and rank them in a descending order. Afterward, the algorithm records the adversarial robustness of each layer and selects the most vulnerable bit in the entire DNN model among the candidate based off all layers. The iterative algorithm terminates when the robustness drop becomes significantly close to an expected value or the accuracy drop becomes higher than the attacker-defined constraint. Our proposed attack is implemented in Python on top of the PyTorch framework. We perform all experiments on an NVIDIA Titan V GPU. We choose two widely used visual datasets for image classification, including MNIST and CIFAR10. For MNIST, we use the well-known Linet3 and FCN2 network model. For the case of CIFAR10, we use the well-known Linet5 and AlexNet network model. For all DNN models, we use 8-bit fixed point number for the DNN weight parameters. In addition, in our experiments, we use two types of DNN models, the original models and the protected one. To generate adversarial examples, to have protected ones, we leverage the widely used deep full adversarial attack tools. To protect DNNs against conventional adversarial example attack, we use the state-of-the-art defense algorithm called traits, which retrain model via a mixture of clean inputs and adversarial example with additional training epochs. Simulation results confirm that our attack can successfully circumvent the state-of-the-art algorithm countermeasure. In fact, flipping a small set of weights bits can result in a significant robustness drop. For example, just flipping 30 bits out of 500,000 bits in Linet model can cause the accuracy of the DNN model drop to 60%. In this figure, we compare the input perturbation vector required to fool the protected Linet on CIFAR10 dataset. Columns A shows the clean inputs, column B shows perturbation vector required to deep fool, and column C shows crafted input for deep fool. Column D shows perturbation vector required by our attack. And last, column E shows crafted input for our attack. As you can see, the crafted input for our attack is very stealthy compared to the state of previous attack. In conclusion, in this paper, we highlighted that protected DNNs are vulnerable to adversaries that exploit hardware-based faults. Moreover, we propose a new stealthy attack that depleted DNN intelligence through smart bit flipping. In this regard, we designed a novel algorithm that enables internal tampering of DNNs in a stealthy way. In fact, our work motivates the need to enhance the robustness of DNNs against hardware-based fault injection in addition to accuracy. Finally, I wanted to acknowledge to all agencies that support this research work. Thank you.